Okay, so I'm César Feniou. So I just finished my PhD with Qubit-Pharmaceuticals and Sorbonne Université in December. And I'm now a full-time research scientist at Qubit-Pharmaceuticals, focusing on quantum algorithms for quantum chemistry. And I used to be an intern, a master's intern in Alex's group during COVID. I wasn't able to get there yet, one day maybe. But this is where all started regarding quantum computing and chemistry. So I'm happy to give this talk today. All right, should I start?
Yeah,
okay. Perfect. Yeah, so today I'll be talking about a research project we've made about quantum algorithms for real-space chemistry on adaptive molecular grids. What I will present is based on a preprint that was out this summer, available on archive with Sorbonne Université and Qubit-Pharmaceuticals. I'll start by briefly give a context to this. I guess most of you are chemists, so I can be quite quick on this. So we're working on the electronic Schrödinger equation. So we have a system of eta electrons and m nuclei that are fixed point charges upon which the electrons move. Their time evolution is given by the Schrödinger equation.
I'm not sure if we see your slide. We still see the title slide. Is it
okay. Okay, then I'll just. Can you see it now?
Yes. Thank you.
Okay, then I'll just move like this. So the electronic motion is given by the electronic Schrödinger equation. We're working with a wave function that is antisymmetric under the exchange of two electrons. This is the usual Pauli principles. The state space is the antisymmetrized tensor product between each single electron space with finite kinetic energy. And what we are looking for as quantum chemists are mostly the bound eigenstates, especially the ground state, which is the lowest energy eigenstate. Of course, the ground states from systems of more than one electrons can't be solved analytically. So we need to find a numerical resolution to this problem, where we first need to give a spatial, to discretize the electronic degrees of freedom. So first, spatially, we usually expand the electron space into spatial orbitals. And we build Slater determinants, which are antisymmetrized products of spin orbitals. So this finite basis set induces a spatial resolution error. And then, given this basis, what we solve is the so-called full CI variational problem. So the full CI space is the full space of all possible Slater determinants. And the full CI ground state is the lowest energy eigenstate in this space.
So I can ask this context: spatial orbitals, are they localized spatial orbitals? So you're doing this effectively on a localized grid, or are they just generic orbitals that, like in quantum chemistry?
So far, it's generical. So far, it's generical. Yeah. So from this point, yeah. Well, of course, I'll be talking about grids soon. So fair point. From this point, a Slater determinant can also be an antisymmetrized product of grid points, for example. So it's just generic spatial orbitals. So one comment on this is that the full CI space grows combinatorially with the system size. What we usually do in quantum chemistry is working with truncated correlation methods, so working on a determinant subspace of this full CI space. And of course, this truncation introduces a correlation error. So it quantifies how much electronic correlation we're able to describe compared to the full CI. So we classify these classical numerical methods using what we call Pople diagrams. So yeah, within the subspace methods, for example, the Hartree-Fock works with only a single determinant. CISD includes single and double excited states from excited determinants from Hartree-Fock. So we have the n to the 4 determinants in the subspace. And there are also other methods with that can be classified of increasing amount of electronic correlation. And what we target is the chemical accuracy, so an error deviation of 1 kcal per mole, which has a physical meaning, from the exact solution. So exact solution in terms of full CI, but also in terms of complete basis set limits, so regarding the spatial discretization. And of course, getting nearby this exact solution gets increasingly hard in terms of computational costs. Especially it becomes exponentially difficult with the size of the system. One comment on this is that the classical computational cost can be framed as this. So we have a subspace and correlation determinant subspace that sets the Pauli n cost in the corresponding methods. And then you also have a cost regarding how much refinement you need to include the correlation. And this cost is highly system dependent, and you have no closed form on the error you make on the correlation error. So this is where quantum computing works a bit differently because as you all know, qubits can encode the exponentially larger determinant space efficiently, and this is the foundational principle that made people think of quantum algorithms to solve the chemical problem. So I only classify the two sort of flagship algorithms for this task. The variational quantum eigensolver, which is a variational problem that also works on a truncated determinant space, and the quantum phase estimation, which is closer in principle to the full CI, where you have in fact a controlled error on the correlation and a corresponding cost that is polynomial in the system size. In the error, but also in the quality of the initial state. So more precisely, the overlap between the initial state and the target ground state. So if we were to classify these quantum algorithms in our diagram, the VQE can be somewhere on this axis. And the quantum phase estimation looks more like an exact diagonalization because you can control the error. And the hope for having a quantum advantage is that these methods have a less increasing computational cost compared to their classical counterparts towards the exact solution. So in either case, we need to map chemistry to qubits. One way to do so is the second quantization. So this is usually the one we start looking at when studying chemical problems on quantum computers. Because there's this convenient mapping between qubit and spin orbital, where qubit in state 1 maps an occupied spin orbital, and qubit in state 0 an occupied one. And so in this mapping, the eta n molecular system is encoded in n qubits. We can represent the spin orbital Hamiltonian, the usual second quantized Hamiltonian, using Fermionic creation and annihilation operator into qubit Hamiltonian that works with a linear combination of Pauli strings. There are a whole range of mappings from Fermionic creation to Pauli strings, including the usual Jordan-Wigner mapping. And then there's also another mapping that is the first-quantized one, where you directly encode the wave function onto the qubit. So we have a single electron state over n grid points or n orbitals that can be stored using log n qubits. And we can build the tensor product between each single electron state using eta log n qubits, so one register of log n qubits per electron, and then we just need to add a layer of antisymmetrization to work in the relevant physical space. But the qubit count is eta log n in this case. And the Hamiltonian is expressed as so we directly discretize the Hamiltonian in the qubit basis, kinetic and potential operator like this. I'll go into more details a bit later. So a word on quantum phase estimation. So the goal of this algorithm is to encode the spectrum of the Hamiltonian into eigenphases that we can measure from the quantum computer. So assuming the following spectral decomposition, the quantum phase estimation looks like this. So we first initialize our quantum circuit. We prepare especially the target eigenstates in psi here. Then we encode the eigenphase. We convert in the ancilla to computational basis using inverse Fourier transform, and we are able to measure and to sample the eigenphases that we are looking for. So the requirements from this algorithm is that we have, of course, since the Hamiltonian is not a unitary operator, we need to find a unitary representation that encodes a function of the spectrum when applied to a ground state or to an excited state, and we must know the inverse of this function. So the usual one is the time evolution operator because it's pretty straightforward. But we'll see just after that there's other options. And we need to make sure that this unitary operator has an efficient decomposition into quantum gates. So constructing the unitary U for QPE, we have the time evolution operator that encodes the eigenphases, but we can also work with a so-called Qubit-ized walk operator, where the function is not the function of the spectrum is an arc cosine, and that works from block encoding of the Hamiltonian, so a unitary block that contains somewhere in the matrix the full Hamiltonian, and we can access the Hamiltonian by doing signal processing on this unitary block. So regarding this method, the block encoding is encoded with a usual method that is a linear combination of unitary. So we first express the Hamiltonian as a linear combination of unitary, for example, in the Pauli basis. We can also define the normalization constant lambda that will be important later, and then we have access to two oracles, so prepare and select, and we can see that applying prepare, select, prepare dagger, or the inverse, we are able to encode the Hamiltonian as a block of a unitary operator. And processing this unitary operator is the way to encode the spectrum properties. So what we're interested in is the cost drivers in this algorithm. So with Qubit-ized QPE, we have a number of queries to the WH, which is the unitary block encoding. Well, not exactly; it's the walk operator that we have from the block encoding, but it's just a few gates more. So the number of queries scales with the subnormalization constant and the epsilon, which is here the correlation error that we target. So the normalization factor lambda corresponds to the one norm of the LCU, and it grows with the coefficient magnitudes in the Hamiltonian. And we also have a cost. So once we know how many times we query WH, we also need to know how many gates we need to encode WH, the work operator. For a k-sparse Hamiltonian, the cost is in the order of the number of LCU terms in the Hamiltonian. So if we're working with basis sets that have a spatial overlap, we have n to the 4 terms. And if we're working with basis sets that diagonalize the Coulomb operator, we have n squared terms in the LCU. For example, plane waves, grids, and more generally any local basis, so such as, for example, wavelets or ghostlets.
César, can I ask where that number of queries comes from? Yeah.
Yeah, so it comes from the fact that the energy you will get out of measurement from QP is the eigenenergy divided by the subnormalization constant. So you'll need to repeat in the order of yeah. So this is alpha, but alpha is equal to lambda. So this is something that is wrong on the slide. But the idea is that you will need to repeat the QPE lambda times in order to get a proper estimate on EK, if that makes sense.
Thank you.
So regarding this qubitized QP, there's a gold standard in the asymptotic requirements in the asymptotic scalings is the first quantized plane wave formalism. So first quantization, as I just told you, we have eta log n qubits in terms of memory, and the Hamiltonian looks like this, so we have the one norm dependence corresponds to the absolute magnitude of the coefficients in the Hamiltonian LCU. And this coefficient, they scale with the minimal spatial resolution h. So for example, the kinetic term is in 1 over h squared, and the Coulombic terms, because of the singular points, are in 1 over h. So overall, the lambda, the normalization constant, is in the order of eta times, because they are single body operators, eta divided by h squared plus eta squared divided by h. And if you're looking at plane waves, you can consider minimal spatial resolution as proportional to a cell that is itself proportional to the number of electrons divided by the number of basis functions that you're using, and up to the one third, because we're working in 3-dimensional space. So overall, the lambda scale as like this. So even though we have a log n contribution in the number of qubits for the dimension of the basis set, we pay well, sublinear cost in the number of basis function, but still more than log. So it's also a complexity driver in the algorithmic costs. Yeah, as I was mentioning, so QP is a full CI level if we want, because we have control on the correlation error, but we have no control on the basis error. So ideally, since n is a cost driver, we'd be happy to get to the exact solution while minimizing the number of basis functions that we're using. So we want each basis function to really improve the spatial resolution of a problem when we add it. And overall, why do we? So now I will be looking more carefully at what we know about the target eigenstate spatially, and why do we need a very sharp spatial resolution, and why it can be a problem in some chemical problems. And this is mostly due to the fact that the Coulomb interaction is singular when the electrons or electron nuclei, when charged particles are at the same place. So the potential look like this if you have a fixed nucleus and an electron going moving in this space. So what this incurs at the wave function level is a cusp behavior at coalescence. So this is what we see here. So it's a really sharp feature that we are able to describe analytically. So we know how it behaves. And we also know that elsewhere the behavior of the wave function is smooth and quickly decaying. So this divergence. So the problem with this divergence is that we will need a high spatial resolution near the singular points, much more than we need far away from this singularity. And well, for fixed nucleus, for fixed nuclei, it's kind of easy to capture, but electron singularities can occur anywhere in space, and also the closer you want to describe the space here, the higher the Coulombic term will be when closing to the singular point. And we know that the quantum phase estimation complexity scales with the norm of the Hamiltonian. So in principle, it seems like there's a trade-off between exploring the singular points and reducing the cost in QP. So as I was mentioning, most first-quantized quantum algorithm use plane waves or uniform grids, which corresponds to a uniform and fixed spatial resolution. And for this chemical spatial resolution, if you want to capture accurately the cusp near the nuclei, you will quickly oversample the low density regions because you span it uniformly, while we actually know where the electronic density is high, and near the cusps we know we need to have some sort of localized basis functions. This is also why we are using mostly Gaussian basis in second quantization. So we can classify the basis sets. So localized orbital is non-uniform, but you have a number of terms, is n to the 4. Plane waves and Cartesian grids are uniform, so they cannot capture efficiently both the tail and the cusps, but you have an efficient encoding of the Hamiltonian. And what we propose in this study is to work with an adaptive grid that keeps the Coulombic term diagonal, so that we have n-squared terms, but that also localize the grid points near the nuclei singular points. So the sketch is that we go from a uniform Cartesian grid into something that looks like this, an adaptive grid. So here it's obviously a sketch of a water molecule, where you will concentrate points where the nuclei are, and the idea is to solve the Schrödinger equation in this basis set.
So doesn't the kinetic energy get a bit messy in that basis, or is it simpler than it looks?
No, you'll see that it's actually harder than it looks. Well, that's actually, that I spent a couple weeks specifically on this, on how to frame the kinetic energy on this problem. So just more precise words on these adaptive grids. The idea is to concentrate grid points where the electronic density is high, so that we capture the electron nuclei cusps. What we took for these grids are DFT integration grids. So this is a quite common problem for DFT quadrature. You want to integrate some functionals over the space. Of course, you will concentrate the points where where you have a high electronic density. But now, in our problem, as you mentioned, Alex, is not only about integrating it's also about solving, so expressing the operators in this basis and applying them. So typically in DFT, they use radial discretization that looks like this. And you have also an angular quadrature, Lebedev, so Baker-Lebedev in this case, that intends to preserve the rotational symmetry of the problem. So here the grid density follows the decay and the cusp structure. And so next, the challenge is to express the Hamiltonian in this adaptive grid basis. And here we are. So standard finite differences in Cartesian grid, it's very easy. We know that the Laplacian is roughly three diagonal because you always know where your neighbor is. You have a very tensorized structure, and this is no longer the case here. Additionally, you have the atom sentence grids that overlap in space. So it's harder to define the nearest neighbors to do standard finite differences. What we could think is express the spherical Laplacians for each sphere, and then apply translations. But obviously, the Laplacian is not invariant upon translations, so it doesn't work. So what we use is what we call a Voronoi. Well, it's called Voronoi diagrams or Voronoi constructions that defines for each grid points a neighboring, so a volume that is allocated to each grid point. It's very basic definition, and it partitions space into convex polyhedra. So here we have a neighboring that is defined geometrically, and we have cells sharing facets on which we can do, in fact, finite volume differences. And this is how we proceed. This definition, this Voronoi diagram definition, is can take as input any grid point, so it's really independent of the underlying grid structure. It looks like this. So you have smaller cells near the nuclei, larger away, and each bit of space is allocated to a cell. So from this Voronoi diagram, we can define a Voronoi cell volume, facets between the cells, and we can express the Laplacian using Gauss theorem as a finite volume Laplacian. So as facets divided by volumes, and also we can see that it's so we have a diagonal term, and we have off diagonal terms as many as each cell has neighbors. So we have so this lambda space corresponds to the neighbors of the cell number n. And one comment on this is that it typically doesn't scale with the number of cells. So we can see that taking any number of grid points, we have a quickly converging number of neighbors in the worst case.
So in this space, that isn't a symmetric operator anymore because of the 1 over Vm, unless I'm missing something. Does that cause problems?
You're always 3 slides ahead.
Okay, we'll get to that.
There's a way to transform this back to a symmetric operator. But yeah, fair point. You have this one where
points whose volume is infinite because they're on the edge of your cell, or the edge of the universe, effectively.
Sorry, say that again.
So there are some points which are the last point away from your atom that are the nearest point to infinity that have an infinite volume. What do you do with them? They just produce a zero off diagonal element.
Well, in any case, it has neighbors, so you can still do finite volumes, forward in a given direction, because you won't have neighbors in the other direction. And I think it wasn't a problem. I remember that compared to finite differences, it's much less critical to deal with the edges. I can't tell you precisely how we dealt with this, but I remember it's better behaving.
I suppose the surface area, which is the bit you're getting wrong, scales less than the volume, you're probably okay.
So as I was saying, the resulting Laplacian is a sparse matrix. So we have at most lambda terms in a line plus 1, and as I was saying, it doesn't grow with n. And the local connectivity in these neighbors is set by the underlying molecular geometry, and plus some parameters on how the grid overlap, things that we can change by hand. So from this we can define the differential operators in the finite volume scheme. So we express the wave function in the Voronoi cell basis. Or discretized molecular Hamiltonian looks like this. The matrix. So we have this Laplacian operator that I just described, and we have Coulombic contributions that are diagonal, given like this, which are quantities that are easy to compute. So it's pretty straightforward. As Alex mentioned, as defined here, the Voronoi Laplacian is not Hermitian, but we can rescale it with a diagonal operator that averages between the volumes of the forward cell and in the neighbor cell and the cell n. And that restores the hermiticity. You just need to pay attention in rescaling the eigenstates that you get. So we have sparsity and locality that are preserved in this case. The degree of sparsity doesn't grow with the total number of grid points. So we were able to express a Hamiltonian that is sparse and Hermitian. So in principle suitable for Qubitized QP. And the question now is, what's the new scaling? And as I was mentioning earlier, the scaling of the norm depends on the minimal separation between grid points. And if you apply a transformation that densify grid points near the nuclei, you will decrease the norm of your operator. So there's an apparent trade-off, as I was introducing earlier. So you have a lower minimal separation distance, and the operator of the Hamiltonian increases. We have a direct impact on the cost. So you cannot decrease the error without decreasing the density of grid points, and inherently it seems to raise the Hamiltonian norm. One thing that we worked on from this is that we know that the cusps they stem from the Coulombic singularities, and in classical chemistry there's a range of techniques that transform at the operator level these singularities in order to improve the spatial resolution of the problem. And this is what we try to include in this work. So it has a name. It's called transcorrelated molecular Hamiltonian. The idea is to eliminate Coulombic singularities, and we proceed by encoding directly the cusps using a so-called correlation function. The transcorrelated Hamiltonian is defined like this. So it's a similarity transformation on the original Hamiltonian. It's a similarity transform, so it's isospectral at the complete basis set limit. We have now an effective bounded potential, and this results in smooth eigenfunctions. So these are sketches. If you apply an effective smooth potential instead of the singular Coulombic potential, your resulting eigenstates are smooth, well behaved, and you even choose how they behave near the singularity in the correlation function.
So, does the transcorrelated potential? Do you have actual plots of the real thing like that, or is that just what we hope happens?
So it will come again. This is what, yeah. So from the equations, you know that you can have an effective potential that looks like this, because you correct the 1/x potential in Coulomb, and you replace it with an effective potential that you choose. You have side effects that I'll give later, but it looks like this, and the eigenstate. Well, in this very easy and specific case, the transcorrelated eigenstate looks in fact like this. So yeah, so a bit more mathematically. So the similarity transform, you can expand this using the commutator formula that goes up to order 2, because we are only dealing with a Laplacian operator. So the correlation factor includes the encoding of the cusps with a nuclei electron, but also the cusps in between electrons. So there are functions of the grid to nuclei distances and grid point to grid point distances. We can choose the form of these functions, J and H. We took some from a paper of one of our co-authors, Emmanuel Giner, that look like this. So in fact, so these functions, they are chosen so that at leading order in 1/x, tau reproduces the effective smooth interaction that is set by typically what we have here. So here we have a Gaussian behavior at singular points. And again, the transcorrelated Hamiltonian is isospectral to H. Yeah, so I won't go into the full mathematical details, but the key idea is that if you develop your transcorrelated Hamiltonian, you have effective two-body terms, and you have also an induced three-body operator that is bounded, and that can be in fact approximated into effective two-body terms. These are some work that are carried out with Ali Alavi at Max Planck, mostly. But the idea is that we can also express this transcorrelated Hamiltonian on the Voronoi grid as a sparse Hamiltonian, because it doesn't change it doesn't act on the basis. So it doesn't change the inner product. It doesn't change the fact that a neighbor is still a neighbor. So you can express it as a sparse operator on the grid. You just have a three-body term, and you have additional differential terms that you need to express in the finite volume frame. So this transcorrelated Hamiltonian, you have, as I was mentioning, a three-body term, and one key property is that it's no longer Hermitian. So we can no longer use the standard quantum phase estimation algorithm, and some work has been carried out on eigenvalue processing operators that are not Hermitian. This is pretty recent, but the asymptotic complexities are similar to those of QP. And one key point is that they are also working based on the block encoding of the Hermitian operator. So it doesn't change much to our framework. It's pretty straightforward to include it to this generalized eigenvalue processing algorithm. So this is a sketch of true results of transcorrelated Hamiltonian on the H2 plus 2D using an adaptive grid basis. So the non-transcorrelated eigenstate looks like this. So you have sharp cusps at the nuclei positions. And then when you apply your transcorrelated, your correlation function, the eigenstates are progressively. So you have also a parameter that controls how you encode your potential, and you can have a more or less smooth expression of the eigenstates. So this is a toy system that combines adaptive grids and transcorrelated Hamiltonian. We wanted to work and to validate the framework on many electron systems.
So in the previous, was there anything stopping your mu going to very, very small numbers? You just get a really boring, very flat thing, or if your mu gets smaller, do you start picking up cusps again, or something?
Yeah. Okay. Yeah. So this is really system dependent, but what can occur, you cannot set arbitrarily low mu, because at some point you will get how to say this. You will get a sort of anti-cusps, so you'll have locally an attracting potential between the electrons, which is much harder to understand physically. So usually quantum chemists prefer to work with reasonable cusps. In our case, what we're looking for is just to have well-behaved eigenstates. We don't need to have it critically flat so far, because we're also using in conjunction with adaptive basis. So it's just about removing the cusps, and there's no much fine tuning on this.
Okay, thank you.
So to validate this, since of course the quantum algorithms we plan to use are fault tolerant and out of reach of current quantum processors, we need to emulate its behavior. To do so, we worked on the non-Hermitian Davidson solver from a software that is developed at the lab at Sorbonne Université. So one first system that we worked on is a system that is quite standard in the transcorrelated literature, which is the helium cusp. So we're looking at an angular cut of the helium ground state that corresponds to this. So we are looking at the azimuthal coordinates and the wave function amplitudes, and when the phi is equal to 0, we have the two electrons at the same sharing the same cell. So in yellow here, you have the non-transcorrelated behavior of the helium ground state. So you have this sharp behavior around 0, and progressively, when you apply mu, you are able to flatten this cusp. And in that case, if you go lower than 0.9, you start to have an attractive behavior, so a higher higher electronic density at the singularities. So this is a pretty sound result. We have a correct cusp behavior. We can easily plot these same curves on different basis sets, and this is quite something that is quite standard, so easy to verify. So in our grid, which was by the way slightly different from the grids I presented before. So here we are tracking specifically this phi coordinate, so we can no longer use a Lebedev quadrature. We need to have a more sort of a Gauss-Legendre, so you need to have a proper theta and phi tensorized form of the spherical grid to track this properly. Another system that we numerically investigated is the hydrogen dissociation. So I guess you're all familiar with this. So the idea is, so we have different geometries for a Noid diagram. we also increase the number of grid points. And what we are looking for is, are we able to improve the correlation error when we get to larger and larger grids? And the second thing is, are we able to dissociate physically our system? We have size consistency at long range.
Are you making use of the cylindrical symmetry in this system, or this is just a full three-dimensional grid?
No, that's a full. I'm not using any sort of symmetry. So yeah, it's just generic proof of principle. It's not about again fine-tuning and striking the best possible result for such a simple system. It's more about testing what this Hamiltonian matrix is getting as ground states over the geometries. So if you look at the scale of the computation, if you have 4,000 grid points, the size of the matrix is 16 millions, because you need to encode the full tensorial space. But quantumly, it corresponds to just 12 qubits per electron. This is the most attractive feature of the first-quantized formalism. So as I was mentioning, we check the size consistency and the systematic improvability when we enlarge the grid. One comment also, it's not perfectly smooth. As you can see here, you have small kinks in the dissociative process. This is mostly due to the fact that when you're using the Voronoi grids, when you shift a bit the position of the nuclei, you can have a completely different Voronoi diagram because of the overlapping regions between the cells, and this may induce the locally positive or negative electronic correlation, but this is only due to geometric stability of the Voronoi diagram. So I think so the contribution of this work it's about providing with a framework that is able to run first quantized quantum simulation in a basis that is different from uniform Cartesian grids or plane waves. So in that case, it is adaptive DFT grids. The formalism we choose to express the differential operator, which is the main concern when shifting from, for example, in the Fourier space, the kinetic representation is straightforward, and the finite difference in Cartesian grid is also pretty well studied. So what we worked on is the Voronoi cell basis plus finite volume differential operators. We are able to have a Hermitian formulation of the Hamiltonian suitable for QP, even though we have this inherent problem of the Hamiltonian norm and the Coulombic singular points resolution. And we try to extend, so to introduce a new paradigm with this transcorrelated Hamiltonian, using a generalized eigenvalue solver on quantum computers. And what we have as remaining challenges in this endeavor is that so far we were working on the Voronoi cell basis that takes as input any grids, but our grids are in fact very structured. It's just centered on atoms. It can be defined in closed form mathematically. So it's pretty clear that if you want to improve the cost of block encoding the operation, we need to leverage this structure, either in an efficient data loading process, or we might be able to also find compressed block encoding. So sort of we won't be able to get a fully three-diagonal structure, but if you're able to find patterns in the non-zero spots in the matrix, it opens the door to more efficient block encodings. one idea is to go fully quantum, to give as input the grid and system parameters, and build the Voronoi diagram quantumly. This is, I think, this can be done with standard reversible arithmetics, because it's only about computing distances. And then you can think of assembling the Hamiltonian directly and block encoding it. And overall, so this transcorrelated Hamiltonian formulation, we need to investigate potential advantages over classical methods, or not classical methods, but over plane wave methods, or even second quantized formalism system-wise through resource estimation. So this would require fine-tuning of the different parameters, and probably a system differentiation for the regimes where we think that plane waves will be working better than localized grids. And for some chemical systems, I mean, whenever you talk to quantum chemists, they are usually working with systems that are locally very strongly correlated, and that are not convinced that even a million plane waves will be able to resolve the interactions they want to characterize. So it's in this very frame that we believe that an adaptive grid basis can work. So yeah, thank you for your attention, and I'm happy to take questions.
I've asked loads of questions. Other people with questions?
And the paper is available for that, is it?
Yeah. So the paper is on archive. I have it here. I can probably show it. Ooh, I can't show it. Well, never mind. Yeah, it's on archive. It's in the first slide here.
Thanks.
You end up with 3 qubit operators because you've got 3 electron operators in there, and does that cause pain?
So yeah, so the 3-body operator gives you so it's bounded and diagonal, so you will get where is it? So yeah, so this 3-body operator is bounded and diagonal, so you just act on 3 qubit registers with a diagonal operator that is bounded and probably easy to block and code.
Okay.
Yeah, but with a couple of discussions from people at Ali Alavi's group, they believe that the 2-body approximation is pretty well suited for this problem.
Yeah, the XTC version probably works quite well on this.
Yeah, I expect it would be completely fine.
But one word on this is it's not so clear. So maybe I put this as a point. Yeah. So okay, you have a 3-body term, so you have a eta to the 3 to the cube interaction, but it's bounded. It can be low, and it's not clear that even asymptotically it will worsen much the results. Because if you're able on the other end to have a much better spatial resolution, or if you're able to work with a much lower n, there might be curves crossing at some point. This is what I was mentioning at last. So depending on the systems, it's just a different way of framing the problem.
Yeah, and results. For what we can be validated experimentally.
Sorry,
Speak up.
Did you try to validate your results experimentally?
Yeah. Well, I actually just did a couple of resource estimates on these very basic systems, and you don't want to know how many gates I needed to block encode the Hamiltonian. I think I think that we'll have experimental results on second quantization earlier than we'll have on first quantization. But I think there's some regime where like small systems with few electrons, but where you need a very high spatial resolution, first quantization regime can take over, but it won't happen before fully fault tolerant, I think.
So one of the challenges with the first quantization regime is because you've got a very compressed representation of where each electron is, you need to access that quite a lot simultaneously to do parallel operations. I think so. Yeah, so you can't parallelize as efficiently as some, but I think maybe that'll be okay eventually. Yeah.
Yeah, no, that's a good point. You need to make assumptions on the fact that you can act in parallel on different registers. That's a key requirement, I think.
Questions? Okay, thank you very much, César.
Thank you.
Very nice talk. Very nice work. I like CH2.
Well, dissociation.
Yeah, exactly. The dissociation of it is very good.
Yeah.
Yeah.
Thank you very much.
Yes.
Well, you have to make,
It's called by someone.
yeah.